Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Sara Kopf and Florian Bourriquen, who have recently authored a ChemRev paper together. Sara and Florian will take turns presenting on different aspects of today's topic, and I think in this way we can get a broad view of where this field stands today. To briefly introduce today's speakers, Sara earned her bachelor's and master's in chemistry from Heidelberg University before doing her doctoral studies first at ICIQ in the Melchiori and Maceras groups, and subsequently in the Beller group at the Leibniz Institute for Catalysis. Florian obtained his bachelor's and master's from the University of Rennes and is also currently pursuing his PhD in the Beller lab. And with that, I'll hand it over to you, Sara and Florian. Thank you for joining us today.
Good morning, Matt, and thank you for these nice presentations and the invite. Indeed, Sara and I want to discuss the recent developments for the hydrogen isotope labeling of organic molecules, as it is the topic of our PhDs here in the Beller group, and also because we recently wrote a review on this topic. We have selected a few representative methodologies that we want to briefly present in this video. However, if one is interested in the topic of deuterium and tritium labeling, I suggest to also have a look at the review where more approaches are presented. Deuterium, being a stable isotope of hydrogen, has seen its use constantly increase over the last years, as you can see here, especially between 2016 and 2020, around 18,000 publications contain the word deuterium. This is due to the distinctive properties of this isotope compared with protium. For instance, in medicinal chemistry, the introduction of a deuterium atom allows for the tuning of absorption, distribution, metabolism, and excretion properties of drug candidates. Indeed, the higher energy required for CD bond cleavage compared to CH bond cleavage, that is called kinetic isotope effect, can improve metabolic stability and allow for lower doses of a given pharmaceutical. In this respect, in 2017, deutetrabenazine has been the first deuterated drug approved by the FDA. Since, a number of compounds containing deuterium atoms are currently in drug development. Other applications of organic molecules containing deuterium atoms are as standards for mass spectrometry or in materials science. For instance, taking advantage of kinetic isotope effects, the properties of organic light-emitting diodes and fluorophores could be improved. For Deuterium Incorporation, different approaches are feasible. Hydrogen isotope exchange is the most investigated method. Here, carefully selected homogeneous or heterogeneous catalysts allows the substitution of hydrogen by one of its isotopes. This approach is highly desirable as it can be applied at a late stage during processes. However, it can be challenging to control radioselectivity as well as chemoselectivity. Plus, in this case, labeled product and unlabeled starting materials are virtually inseparable. Therefore, HIE approaches have to be highly active. This is also the reason why Deuterium incorporations in HIE methodologies are presented providing the percentage of deuterium incorporation at one specific position. This being said, most of the currently developed HIE approaches permit deuterium incorporation above 90%. On the other hand, with the other main approach, that is reductive deterioration, quantitative deuterium incorporation are frequently encountered, owing to the intrinsic mechanism of such reactions. Here, deuterodehalogenation is the most commonly encountered, but reductive deuteration of groups such as carbonyls, alkene, alkynes is also reported. The main limitation of deuterodehalogenation is the availability of the substrates. When aryl and alkyl halides are broadly available as simple building blocks, for more complex molecules, an additional pre-functionalization step can be required, namely the introduction of the halide. And in this case, HIE is often the method of choice. You can see here two graphs presenting the price per mole and the number of recent reports using common deuterium sources. Deuterium oxide, D2O, being the parent of all the other deuterium sources, is by far the most affordable and therefore the most desirable deuterium source to use. Deuterium gas D2 is also frequently encountered, especially when using molecularly defined catalysts that are often not stable in presence of heavy water. You can also see here that a number of deuterated analogues of common reagents are commercially available, such as, for example, sodium borodeuteride, and these can be used the same way one would use non-deuterated equivalents in a multi-step approach. Regarding tritiation reactions, the preferred isotope source is T2 in order to prevent the use of toxic T2O. Hence, D2 is used during optimization studies. Now, Zaha will start with recent developments on HIE, especially focused on those using homogeneous catalysts.
Thank you, Florian. The development of hydrogen isotope exchange, or HIE methodologies, is closely intertwined with the field of transition metal catalyzed CH activation. And the most established way of introducing deuterium atoms into organic molecules is based on iridium catalysis. It can be applied for the labeling of aromatic substrates that exhibit directing groups. Originally, this methodology was mainly thought for tritium labeling, and accordingly, in the early days, isotope chemists were especially looking for ways of activating deuterium gas for isotope exchange. In the last century, the Crabtree catalyst was found to be active for that, and following this discovery, a lot of research, particularly from the Kerr group, has gone into finding more active catalysts for this transformation. The result is a family of NHC and phosphine-ligated iridium complexes that enables HIE of many substrates under ambient conditions. It is now the most widely used catalyst family for HIE, but other notable catalysts have also been developed, for example by the Pfalz group in collaboration with Roche, as well as more recently by the Tamm group in collaboration with Sanofi. As the importance of deuteration in itself, rather than just as a model reaction for tritiation, grew, attention has been paid to the replacement of deuterium gas by cheaper and more easy-to-handle liquid deuterium sources, especially heavy water. Besides, a current focus of HIE research has been the replacement of iridium by more cost-efficient transition metals. However, although some progress has been made in this regard, the really mild conditions and high deuterium incorporations that can be achieved with iridium have not been met yet by alternative catalysts. Over the years, a variety of native directing groups has been exploited for HIE. Lately, a focus of research has been placed on the utilization of weakly coordinating functional groups such as carbonyl functionalities. Heteroaromatic compounds such as indoles that contain directing groups have also been widely explored for HIE. Two types of directing groups that have been particularly difficult to activate previously have now joined the list of amenable substrates for HIE, and we're going to have a closer look at them now. The first ones are sulfur-containing functional groups, which are an important structural moiety in many drugs. Due to the sterically challenging tetrahedral shape of sulfonamides and sulfones, harsh reaction conditions were required for the deuteration of these substrates and often delivered only low deuterium incorporation. But in recent years, sophisticated catalyst design enabled the labeling of these substrates under mild conditions and with high deuterium incorporation. The first breakthrough was achieved by the Kerr group in 2015. They had the idea to use a precursor to the actual Kerr catalyst, where the phosphine ligand is replaced by a chloride. This iridium complex is much smaller than the more typical catalysts and might therefore deal better with sterically difficult substrates. However, by now the methodology was still limited to primary sulfonamides, and secondary and tertiary sulfonamides as well as sulfones remained challenging substrates. Later, the Kerr group hypothesized that even more steric room for bulky directing groups can be created when tethering the NHC and the other ligand on the iridium center to force them away from their otherwise preferred trans conformation. In line with this hypothesis, the Tamm catalyst was used by Derdau and co-workers at Sanofi for the successful labeling of secondary and tertiary sulfonamides under mild conditions. For these sterically hindered directing groups, substrate coordination can replace CH activation as the turnover limiting step. Following this idea, the Kerr group chose to investigate a range of tethered iridium complexes computationally, analyzing their coordination enthalpy. Using a range of catalysts exhibiting different tether sizes as well as steric and electronic parameters, they could then identify some structural parameters that appeared to be beneficial for lower binding energies. The best predicted complexes were then synthesized and tested in HIE reactions and indeed performed significantly better than previous catalysts. Further optimization of the solvent to chlorobenzene afforded an efficient methodology for the deuteration and tritiation of aerosulfones. Another substrate class that became accessible for HIE reactions in the past years are anilins. Ortho-directed CH activation with anilines is difficult as the corresponding metallar cycle would be highly strained and due to catalyst poisoning. As a result, efforts to label anilines have focused on transition metal-free methods under harsh conditions. However, ortho-selectivity is usually not achieved this way, and deuterium incorporations often remain low. Thanks to a recent study from Peters, Chaudret, Derdau and co-workers, this is now a problem of the past. Air-stable NHC-stabilized iridium nanoparticles could be used for the orthoselective deuteration and tritiation of anilines. Compared to ruthenium nanoparticles, iridium nanoparticles show a high chemoselectivity without reduction of the aromatic ring. Shortly after, the labeling of primary anilines under deuterium gas atmosphere using molecularly defined iridium complexes exhibiting mesionic NHC ligands was published by Zhao, Yan and co-workers. As a strong dependence on the presence of potassium was observed experimentally, the authors propose an outer-sphere coordination via non-covalent interactions. This seems plausible as the strained cyclometalliated intermediate otherwise required for orthofunctionalization is circumvented this way. More recently, the same group extended this methodology to phenols, which are similarly difficult to employ as directing groups. An outer-sphere coordination pathway is proposed again, and this time backed up by DFT calculations. The fact that a plethora of native directing groups can now be used for HIE and often with similar catalysts can lead to practical problems. Several coordinating groups present in a complex substrate can compete for directing the labeling reaction. This can make planning of the labeling process of these substrates complex, which is why some studies have devoted themselves to the prediction of the main labeling sites in such cases. For this purpose, Derdau and co-workers have performed extensive intermolecular competition experiments using the Kerr catalyst with equimolar amounts of two directing groups and compared the results with kinetic and thermodynamic DFT data on the reaction. In doing so, they found out that directing group strengths correlate well with the relative free energy of the iridium substrate coordination complex. In other words, binding of the directing group to the substrate is the step that most determines selectivity. Only if the two directing groups form similarly stable complexes with the catalyst, the activation barrier for the CH insertion step governs selectivity. Of course, these results from intermolecular experiments can lack transferability to intramolecular competition of two directing groups within the same substrate, and calculations on the specific substrate of interest are needed for really accurate predictions. While a lot of exciting developments have happened in the field of directed aromatic HIE, and quite some problems have been solved as we have just seen, a remaining issue is the current limitation to labeling in the ortho positions. Drawing inspiration from the field of remote CH functionalization, the first reports on meta-selective HIE have been reported recently by the groups of Mighty and Dye and use Palladium Catalysis with template directing groups to circumvent ortho-metallar cycle formation. Looking at the non-native directing groups required and the expensive deuterium source in this slide, it becomes evident that improvements are required in the context of remote deuteration. It seems that this field is more successfully tackled by non-directed approaches, an area that is becoming increasingly important. Non-directed HIE is not as mechanistically homogeneous as directed HIE, and more sustainable non-noble metal catalysts play a bigger role here. In this field, not only does the absence of a directing group make the CH activation more difficult, but it also calls for alternative means of selectivity control. There is a range of possibilities for controlling selectivity based on pre-existing functionality in the substrate, and this is how we organize this chapter in our review. One way of achieving selective non-directed HIE is by harnessing electronic bias in the starting material. Electron-rich positions, for example, can be targeted mainly by acid catalysis along with protic deuterium sources, especially D2O, whereas electron-poor positions are often accessed using base-mediated but also silver-catalyzed processes and use D2O or deuterated DMSO as deuterium sources. For the latter, milder conditions can be maintained when using transition metal catalysts such as copper and nickel. A particularly mild and effective nickel-catalyzed methodology for the deuteration and tritiation of electron-deficient azenes was presented by the Cherry group. It employs catalytic amounts of diimine-ligated nickel dimer, which can dissociate to monomeric species by coordination of nitrogen-containing substrates. In the following, positions in proximity to the nitrogen atom are labeled with deuterium or tritium gas. When a bulkier ligand is used, dissociation of the dimer is facilitated and doesn't require pyridine coordination anymore. Now more substrates as well as other electron-poor positions can be labeled as well. It goes without saying that electronically controlled HIE reactions are limited to specifically activated substrates. This is not the case for steric control. In this context, iron catalysts have been designed by the Deuterium group that can deuterate and tritiate positions that are remote from any substituent under mild conditions. Deuterium or tritium gas do not only function as isotope source here, but also activate the pre-catalyst, leading to a dihydride as a catalytically active species. Recently, an alternative catalyst was presented by de Ruyter and co-workers. In this case, the active dihydride is directly supplied to the reaction mixture, obviating the need for gaseous isotope sources. These methodologies are not only attractive due to their complementary selectivity to other labeling approaches and their good performance, but also because they use an earth-abundant transition metal. This is, however, accompanied by the drawback of an air and water-sensitive reaction that requires skilled handling. We have spent quite some time now discussing HIE of aromatic substrates. However, non-aromatic substrates, and among these especially aliphatic compounds, are becoming increasingly important. For a long time, aliphatic labeling has mainly focused on two activation principles. Firstly, the exploitation of activated, particularly acidic positions, for example in the alpha position of carbonyl compounds, and secondly, the application of the hydrogen autotransfer concept to the labeling of aliphatic alcohols and amines by oxidation to the corresponding carbonyl compounds and subsequent reduction with a deuterium source. While some new research in these areas has appeared, more groundbreaking new developments for aliphatic HIE have emerged in two other areas that we will look at now. In this context, experience from aromatic-directed HIE, as well as aliphatic CH functionalization, have recently been applied to aliphatic HIE. For example, direct use of the Kerr catalyst for aliphatic amines equipped with a pyridine-directing group, or to more weakly coordinating and thus more challenging aliphatic amides under classic iridium-catalyzed HIE conditions led to the labeling of these compounds in the beta position. For the even more challenging carboxylic acid directing groups, it only makes sense to move to Palladium Catalysis, where a lot of experience in aliphatic CH functionalization has been gathered already. In doing so, and by using diamine-derived ligands, Van Gemmeren and co-workers could recently establish a protocol for carboxylic acid-directed HIE in terminal and even in internal beta positions. As can be imagined, this field still offers a lot of room for more developments regarding different selectivities and accessing more directing groups. The other big development of the past years concerns the use of Photoredux Catalysis for the labeling of aliphatic amines. The Macmillan group pioneered this approach by combining two well-established reactivity modes of Photoredux catalysis, namely the oxidation of alkylamines and hydrogen atom transfer catalysis. Mechanistically, bulky thiol HAT catalysts exchange with deuterium oxide or tritium oxide, while the amine substrate is being oxidized to an alpha amino radical by the photocatalyst in its excited state. This intermediate will then abstract the deuterium or tritium atom from the thiol, affording the labeled product. The resulting thiol radical is subsequently reduced to regenerate both HAT and photoredox catalysts. This way, several deuterium or tritium atoms can be incorporated in each substrate. The main drawback of this methodology is the use of tritium oxide, which goes along with considerable safety concerns. Accordingly, a significant improvement was recently published by a group of scientists at Merck who used tritium gas in a photoredox catalyzed amine deuteration and also showed that thiol catalysts are not the only applicable HAT agents for hydrogen isotope exchange. Instead, they use a rhodium hydride, which plays the dual role of activating tritium gas and transferring a tritium atom to the intermediary alpha amino radical. Following these two pioneering developments, it is expected that photoredox catalysis will lead to more unprecedented HIE reactions on other aliphatic substrates in the future and will really enrich the field. At the same time, heterogeneous processes have really gained importance, and Florian will now tell you more about this.
Thank you, Sara. Indeed, the field of heterogeneous catalysis is of interest in deuterium labeling due to the inherent advantages of such catalysts. For example, their simple separation from reaction mixtures and potential recycling. In comparison with homogeneous catalysis, where systems are usually selective for the labeling of specific positions, with heterogeneous systems, it is easier to present the deuteration techniques by metal. Hence, I'll start with noble metals and continue towards base metals. Common commercially available supported catalysts, palladium and carbon and platinum and carbon, are frequently used for Deuterium Incorporation in presence of hydrogen and deuterium oxide. This combination allows for the in situ generation of deuterium gas that can subsequently be used for the reduction of unsaturated bonds or HD exchange reactions. As is highlighted here with the labeling of ibuprofen, the use of platinum favors HD exchange at aromatic positions when palladium is more selective towards the aliphatic ones. Stepwise sequences or concurrent use of both materials is feasible for complete deuteration of numerous compounds. The selectivity of palladium heterogeneous deuteration can be tuned by the use of custom-made nanoparticles. In fact, as you will see, an emerging trend in deuterium labeling is the use of PVP, polyvinyl pyrrolidone, or N-heterocyclic carbenes to stabilize active metal centers and regulate their activity. In this case, highly selective pencillic deuteration is feasible with palladium nanoparticles supported on PVP and deuterium gas as isotope source. Noteworthy, tritium gas can be used instead, providing tritiated compounds. Next, here's the importance of ruthenium for isotopic enrichment. The group of Sachiki, who developed most of the heterogeneous palladium and platinum methodologies, showed the potency of ruthenium and carbon for the alpha deuteration of alcohols in D2O. Due to the racemization observed when this reaction is performed using chiral alcohols as substrates, as well as traces of ketones detected during the course of the reaction, dehydrogenation followed by reduction of the ketone is likely to take place here. However, a direct CH insertion mechanism cannot entirely be ruled out. The same catalyst permits the Deuterium Incorporation at the alpha position of sulfur atoms. Here, a 4-member dimetallocycle is suggested as key intermediate. In addition of the commercially available ruthenium and carbon, PVP-stabilized ruthenium particles were applied for the labeling of a diversity of nitrogen-containing compounds such as pyridines, quinolines, indoles, and primary, secondary, and tertiary alkyl amines. High selectivity for the exchange next to the nitrogen atom suggests a nitrogen-ruthenium coordination followed by a cleavage of CH bond and subsequent addition of a deuteride. Further works showed the enantiospecificity of this catalyst for the labeling of chiral amines, as well as its performance for the deuteration as well as tritiation of nucleobases. Ruthenium and carbon is well known as hydrogenation catalyst. In presence of gaseous deuterium, reductive deuteration of arene rings is therefore feasible with concomitant labeling of the benzylic position and to a smaller extent of alkyl chains. The effect on the arene ring can, however, be tuned by the addition of sterically demanding and heterocyclic ligands. Indeed, this strong NHC coordination at the surface of the ruthenium catalyst prevents the pi coordination of aromatic rings of the substrate, but not side-on approaches, and coordination of oxygen and nitrogen atoms, therefore directing CH activation processes. A similar tunable reactivity with NHC ligands is feasible using nickel catalysis too, and was reported for the alpha heteroatom deuteration of heterocycles. Depending on the bulkiness of the ligand, the concurrent labeling at the ortho position of adjacent rings can be switched on or off. In this respect, the steric hindrance induced by the ISI ligand would allow substrates to approach the nickel surface through the pyridine ring and on, as depicted here in red, whereas the greater available space of the catalyst surface could allow side-on reactions or even flat coordination of the aromatic ring, here in green. Supplementary to the noble metal and nickel-based systems, our group very recently showed the potency of an iron-based material for isotopic labeling. Supporting a simple iron salt on a broadly available biopolymer, cellulose, followed by pyrolysis at 1000 degrees under inert atmosphere, led to an active catalyst that could be used for the labeling of heteroarenes, including anilines, phenols, indoles, and other heterocycles. From a mechanistic point of view, a radical mechanism is taking place here. we suggested a concerted mechanism in which D2O is split homogeneously by the iron catalyst, yet the resulting radicals are not liberated into the solution, but remain adsorbed on the catalyst surface as activated D and OD radicals. The OD radical abstracts a hydrogen atom from the phenyl ring, forming HDO and the corresponding phenyl radical, which is subsequently deuterated.
Let's now move to a different aspect of isotopic labeling, reductive deuteration or tritiation. This field lends a lot of expertise from hydrogenation chemistry, as it can involve the reduction of carbonyl groups or unsaturated carbon-carbon bonds with a deuterium source, but it also includes deuterodehalogenation reactions. In most applications, a rather old system is still in use, palladium on carbon with deuterium or tritium gas. However, this bears chemoselectivity issues, as olefins and halogen substituents can be reduced at the same time. Besides, in the presence of any source of protons, and this can include labile heteroatom H bonds in the substrate, the activity of the palladium on carbon method suffers drastically. This leads to strict requirements for dry conditions and potentially pre-exchange of labile protons in the substrate. Consequently, it is not surprising that more modern techniques have been developed to circumvent these problems. We'll start our discussion of reductive deuteration methods with deuterodehalogenation. The methodologies that are used within this field depend massively on the type of substrate. For alkyl halides, most reported modern methodologies depend on radical reactivity, whereas previously alkyl lithium or Grignard reagents have been used. For example, the use of diols as deuterium atom carrier, that we are now quite familiar with, has been used in a deuterodeiodination protocol in which a radical chain process is started by triethyl boron. Techniques for aryl or vinyl halide deuterodehalogenation are more varied and can, for example, use transition metal catalysts with organic sources of deuterite or organic reductants such as silanes or superelectron donors along with deuterated solvents. However, it is notable that many new methodologies for the deuterodehalogenation of aryl halides use photocatalytic or electrocatalytic processes. This way, transition metal catalysts are often still part of the process, but more available deuterium sources such as simple deuterated solvents can be used because light or electricity play the role of the reductant. In contrast to photochemical methods where aryl radicals abstract deuterium atoms from the deuterated solvent, for electrocatalytic deuterodehalogenation, or also for heterogeneous photocatalytic methods, the involvement of deuterium radicals from reduction of D2O is proposed. A lot of research has also gone into the deuterodefunctionalization of pseudohalides and other functional groups such as boronic acids, carboxylic acids, and diazonium salts. In this context, a very recent report from the Ritter lab in collaboration with Roche is particularly noteworthy. Using their thioethynation technology, they can perform palladium catalyzed deuteration and tritiation in the presence of gaseous isotope sources, which is in sharp contrast to the deuterodehalogenation methodologies that we have just seen, and at the same time brings advantages over the palladium on carbon method, as the new reaction is much more robust and chemoselective. Mechanistically, dideuterium or tritium coordinates to palladium prior to oxidative addition of the thioetherium salt, but it does not perform oxidative addition itself. Only after oxidative addition of the substrate, which leads to a cationic palladium complex, palladium hydride is formed by base-mediated deuterium or tritium splitting at the palladium complex. The product is then released by reductive elimination. Let's move on to the remaining types of reductive deuteration. Given the diversity of carbonyl functional groups, a range of transformations can be used for carbonyl reductive deuteration. Esters, amides, and nitriles are commonly reduced to alpha-deuterated alcohols or amines. Traditionally, sodium borodeuterite is used for this reduction, but more recent methodologies use ranionickel with in situ generated deuterium gas from the electrolysis of heavy water, samarium iodide as reductant with D2O, or sodium dispersions in deuterated ethanol. More unusual is the complete reduction of esters to trideuteromethyl groups as investigated by the Newman group. Here, an uncatalyzed addition of a deuteride from a deuterated silane to the ester leads to acylated benzyl alcohol, which is subsequently reduced by nickel catalysis. The scope of this methodology was recently extended to the reduction of aldehydes, ketones, and even alcohols. These substrates can alternatively be reduced by a palladium catalyzed methodology from the SU group that allows for the use of D2 or D2O with in situ generation of D2 by electrolysis, depending on the needs of the specific application. Just like other reductive deuteration reactions, the reductive deuteration of olefins and alkynes is less a dedicated research area and rather an application of hydrogenation chemistry. Nevertheless, some specific challenges, such as the exchange with product sources in the reaction media, apply, and some dedicated papers are published. Recent developments in this field include electrochemical and biocatalytic reductive deuteration of olefins and alkynes. In a recent example on the reduction of alpha-beta unsaturated carbonyl compounds by the Chem group, a nodic oxygen revolution occurred and made reductants unnecessary. Similarly, for alkynes, electrochemical methods for the semi-hydrogenation as well as complete deuteration have been reported by the groups of Zhang and Bedinget. A topic that is certainly not borrowed from classic hydrogenation chemistry is hydrodeuteration. In the past years, an increasing amount of groups have worked on the selective introduction of a protium atom on one side of an olefin and a deuterium atom on the other. Reduction reactions with defined heterolytic mechanisms are ideally suited for this endeavor. The Österreich group started this research line by using specific cyclohexadiene derivatives that can selectively hydrodeuterate or deuterohydrate olefins under Lewis acid catalysis via Wieland cations. Later, an ammonia-borane reduction system developed by McGregor, Webster and co-workers could be used for the same reaction under iron catalysis, although some selectivity issues exist for the system with electronically biased styrene substrates. The most accessible isotope sources for hydrodeuteration so far have been reported by the Clark group and require copper catalysis. Here, hydrocupration with a non-deuterated silane as hydride source leads to a cuprate intermediate that is subsequently cleaved by deuterated ethanol.
In addition to the works presented earlier, numerous other methodologies for deuterium incorporation exist, and due to their mechanism cannot be categorized as hydrogen isotope exchange or reductive deuteration. Among them, the field of trideuteromethylation and tritium methylation is of interest as it allows the simultaneous insertion of a label, deuterium or tritium, and the methyl group, one of the most common fragments encountered in biologically relevant molecules. In this respect, new methodologies exist to eliminate the use of stoichiometric amount of toxic reagents such as trideuteromethyl iodide. For instance, the Reductive group reported this air and moisture stable manganese precatalyst for the selective alpha-methylation of aromatic and aliphatic ketones. Via initial methanol dehydrogenation, subsequent aldol condensation, and final hydrogenation, different isotopomers are generated based upon the use of methanol, methanol D1, D3, or D4. A similar tunable methodology is based on a heterogeneous catalyst, here for the insertion of trideuteromethyl groups in amines. Here, the supported palladium photocatalyst is activated by visible light and permits the dehydrogenation of methanol that condenses with an amine, followed by hydrogenation of the imine by hydrogen generated in situ. In order to make the insertion of trideuteromethyl groups more accessible, novel methylating reagents exist, taking advantage of more classic and stoichiometric organic chemistry. One of them is the DMTT, easily synthesized in 2 steps from common reagents and taking advantage of deuterated methanol as isotope source. Using this air-stable compound, trideuteromethylation of carboxylic acids, phenols, sulfonamides, and thiol is feasible, depending on the condition used. Notably, for this procedure and the other trideuteromethylations previously discussed, the isotope incorporation is virtually quantitative and only limited by the deuterium content of the commercial isotope source used, usually above 99%. In the case of tritium methylation, the main recent breakthrough is the work of Macmillan for the labeling of pharmaceuticals using concomitant Photoredux and nickel catalysis. Visible light excitation of the iridium photocatalyst leads to a single electron species that oxidizes bromine, a dissociable ligand from nickel. Hydrogen atom abstraction from tris-trimethylsilane and subsequent abstraction of the bromine from the in situ form tritiated bromomethane generates the active nucleophilic tritiated radical. Simultaneously, the nickel catalytic cycle takes place, with the oxidative addition into the bromine-containing drug and capture of the tritiated radical. Reductive elimination leads to the desired product, and final single electron transfer closes both catalytic cycles. This approach is, by the way, also feasible at aliphatic positions. To conclude our presentation, here is ibuprofen, the 29th most commonly prescribed drug in the US in 2019. Around are some labeling patterns achievable on this simple molecule. Both aliphatic and aromatic deuteration is feasible with specific ortho or meta labeling. Same for the benzylic position, with or without simultaneous aliphatic labeling. These approaches are based on organometallic catalysis and nanomaterials, although novel tactiques relying on electrocatalysis and photocatalysis are also part of the labeling toolkit. In terms of isotope source, the majority of the method now rely on either deuterium gas or deuterium oxide, the most desirable source of deuterium. In the same way, since the early days of isotope labeling, iridium has been a metal of choice. Yet, nowadays continuously more reports take advantage of base metals, such as iron or manganese, as greener alternatives.
Thank you for joining us for this Research Spotlight episode, and thank you to Sara and Florian for a very thorough and interesting presentation. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast. And feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.